Okay. When two chords intersect in the interior of a circle, each chord is divided into two segments. Let me get this to match. Come on. And those segments are called the segments of the chord. So if you look at the picture below, you have this chord, say, right here, but the segments of it would be R and S. The segments of the other chord would be T and U. Theorem 10.14. If two chords intersect in the interior of a circle, then the product of the lengths, not enough room there for me, of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So I could say that T times S, oh, it's not T. That is R. Need to fix my glasses. So let me start over. R times S would equal T times U. Pretty cool. Tangents and secants. So remember, a secant segment is a segment that contains, so a secant would be, you see the whole thing here? A secant segment is a segment that contains a chord of the circle and has exactly one endpoint circle outside the circle. So there's the endpoint. The part of a secant segment that is outside the circle is called the external segment, which makes it external, means outside. So this piece here that's in red, that's the external segment, and it's part of the secant segment. And then here we have our tangent segment. So theorem 10.15 says segments of secant's theorem says if two secant segments share the same endpoint outside a circle, then the product of the lengths of one, we're going to squeeze a secant segment, so secant I'm really squishing it in there. And its external segment equals the product of the lengths of the other secant segment and its external segment. Now, if you're saying, what the heck does that mean? Well, let's see how I do my circle drawing. So here's a circle. And say I have, here's one secant. And here we go. We'll have another one here. And I'll try labeling them. So if this is A, B, C, we'll call this D and E. What this is saying is the external segment here, so AB times the whole secant segment, so AB times AC, so the outside piece times the whole thing would be equal to the outside piece of the other one times the whole thing. So external times whole thing. Right? So piece times whole thing is equal to piece times whole thing. Again, pretty cool. Theorem 10.16. Segments of secants and tangents theorem. Say that 3 times fast. If a secant segment and a tangent segment share an endpoint outside, so endpoint outside a circle, then the product of the lengths of the secant segment and its external segment equals the square of the length of the tangent segment. So in this one, as you see here, here's our tangent and here's our secant. What this is saying is it's labeled here that tangent segment, EA squared, right, is equal to EC times the whole thing. So the part times the whole is equal to this part squared. All right, so that's 3 new theorems. Let's see how it works. All right, solve for x. Well, this was our first theorem, 10.14. So this one, for number 1, we say, okay, the two pieces, 3 times x equals 6 times 4. So 3x equals 20. 24. Therefore, x must equal 8. Here, let's have some fun with quadratics. So the small piece. So 4 times 3 is equal to x times 8 minus x. Okay. 12 equals, distribute, 8x minus x squared. Now, normally I would move the 12 over here, but see that negative sign in front of the x squared? I don't want that, so I'm going to move everything to the other side. I get x squared minus 8x plus 12 equals 0. Because when we're factoring, it has to be set to equal first, so we can find all values for x. Now remember, I'm going to find the factors of 12 that have a sum of negative 8. If you both, right, they both have to be negative to get a positive here when I multiply. So I get x minus 6, x minus 2 equals 0. Now I've set this equal to 0, that equals to 0. What you should get is that x could equal 6 or x equals 2. Both would work. Right? Yeah, I have no negative values here. All right, this one we can skip because we actually just did it. It's a double. All right, now we're looking at our external pieces. So for this one, now this is telling us that 12 is the measure of the whole thing, 8 is the measure of the whole thing in this one. Okay? So remember, this is where piece times whole, piece times whole. So this one would be x, 8 times x, so the whole times the piece, equals 4 times 12. So we get 8x equals 48, x equals 6. Okay. Okay, another one dealing with our pieces. Oh, this time it's not telling us the whole. So for this piece, the whole would be 6 plus x times the piece, which is 6, must equal 5 plus 7, which is 12, times the outside, 5. All right, so now I'm going to distribute, and I'm going to get 36 plus 6 times x equals 60. Subtract 36 from both sides. You get 6x equals 24. X equals 4. Right, so piece times whole, piece times whole. Okay, so here where we have our tangent and our secant. All right, so this piece squared, so 6 squared equals piece times whole. So 9 is the whole, x. So 36 equals 9x, x equals 7. All right. This one, same kind of setup, right? This squared, so 20 squared equals, well, the whole piece would be 4x plus x, right? Because it's not indicating that either one of these is a whole. It's saying these are each the pieces, right? So 4x plus x times the outside piece, right? So I can say 400 equals 5x, right? And combine like terms times x. So 400 equals 5x squared. Right, so from here you want to divide by 5. Right, and I'm going to move it this way. And I get 80 equals x squared. Now you know I like my square roots in exact form. I'm going to take the square root of both sides. And I get x equals, well, 80 is 16 times 5. So I'm going to say it's 4 square root of 5. And now let's do some deep thinking. We want to find the measure. We'll start with finding the measure of angle PQR. Okay. Well, I see that PR is the diameter of a circle, right? If this is a circle O, I know it is. It goes through the center. If that's the diameter, then I know this must be a right triangle. So the measure of angle PQR must be 90 degrees because that diameter would be the hypotenuse. All right, the second question it asks is, use a geometric mean theorem to write a proportion involving the lengths of triangle PQR. Oh, you have to remember something from the last unit. Okay, so the geometric mean theorem says if you had the altitude, you can say that the measure of the legs, so OP, over that altitude, is in proportion to OQ again over OR. All right, so now you remember the geometric mean theorem. Here's our proportion. And if you look at it, so you're saying, let's move over here, OP, so the short leg to the long one of this little triangle is a proportion with this triangle short to the long, OQ to OR. All right, now we're going to need some room to explain number 3. Explain how the theorem involving segments of chords can be used instead of geometric mean theorem. If you look at your notes, theorem, the segment of chords was the first one. So I think it's 10.14. All right, so these would be internal chords. Now, by the segment of chords, it says that if I took the products, right, OP times OR would have to be equal to OQ times OS, right, the products. Now you're told in the diagram that OQ equals OS, right, they're congruent. So OP times OR is equal to OQ squared, right? If I were to write these two would be the same. Which would be the same, so that'd be the same if we did the cross products. Right? If we took our proportion in number 2 and did cross products, we would get the same thing. All right, so there we go. It'd be the same thing. All right, well done. Here, put a little smiley for Ryan. You're doing awesome. Keep up the good work. You can use the rest of class time to complete your assignment from section 6. It's posted in Classroom. I have also created Intervention Lab sign up if you want to meet with me individually for any extra help. We will be meeting on Wednesday to go over what will be on your quiz on Thursday. And I hope you're doing well, and I'll see you soon.